Earlier, we looked at the diffraction pattern through a single slit. Now we're going to look at the diffraction pattern through a circular aperture. This is important because the microscope and the telescope both basically have objective lenses that act as a circular aperture. Now, looking at the circular aperture, the diffraction pattern, we can see that it looks like a bullseye pattern. There's a bright central region at the center, and then that's surrounded by rings which make it look like a bullseye. This is known as an airy disk and is common for any type of Fraunhofer diffraction, that's far field diffraction, for a circular aperture. Now, most of the light is actually contained in the central disk. In fact, about 99% of the intensity is in the central feature, so we normally ignore the outer rings. If we look at the intensity, and assign an intensity value of 1 for the center of the disk, the next ring only has an intensity of 1.75% that intensity. Going to the second ring, we have even less there. And again, integrating over the entire size of the central disk, you probably have more than 99% of your energy in that central disk compared to the outer rings. In terms of the size of this airy disk, we're really interested in the first destructive interference zone, the first minima. And this happens at an angular distance where the sine of the angular size is equal to 1.22 times lambda, the wavelength of light, divided by the diameter of the circular aperture. If we can look at 3 different wavelengths of light, we can see that the airy disk, the pattern, the size of the disk, changes with the wavelength of light. In this first example, we have a wavelength which is actually in the ultraviolet part of the spectrum. At 325 nanometers, the central diameter, the 1.22 times the wavelength divided by the diameter of the disk, the opening, is 440 nanometers. Jumping to green light at 532 nanometers, the airy disk would be 720 nanometers. Going even larger to red light at 785 nanometers, the airy disk would be about 1 micron. So you can see here that the wavelength of light does play a role in how large these diffraction patterns become. This is very important in terms of resolving an image, because the image itself is made out of an infinite number of airy disks generated by the objective lens of either the microscope or the telescope that we use, or our own eye. The intensity as a function of angle looks something like this. And again, you can see the central airy disk right here. The first minima is right here, and then you have the first ring around that. Now, this function looks a lot like we had for the single slit. The main difference is, instead of sine, we use a rather obscure function known as a Bessel function. This is actually the Bessel function, the first order Bessel function. And if we graph the Bessel function with sine, we can see that there's some similarity between the two. They both are solutions to differential equations of the second order. This yellow equation right here is the differential equation from which we get the Bessel functions, or what we should say the Bessel function is a solution of. And you can see it does have this oscillation much like sine does. It doesn't have a constant period, though. You can actually see the maxima actually change in terms of their spacing, and also their amplitude's a little bit different. But again, like sine, this is an odd function. The Bessel function that we're going to use here is also an odd function. Now, when coherent light passes through the circular aperture, and we form this bullseye right here, all right, we're typically creating a diffraction pattern with a very, very small angle. That means that we can make a small angle approximation here. And instead of using sine theta is equal to 1.22 times lambda over the diameter, okay, to determine the size of the central disk, we can make the approximation if we use radians that theta is equal to 1.22 times lambda divided by d. If we take this where we're projecting this onto a screen and large d is equal to the distance to the screen, we can change this such that y, the distance from the center of the disk to the outer edge to the minima, is 1.22 times lambda times the distance d to the screen divided by small d here, which is the diameter of the opening. The small d is taken to be much, much smaller than large d. Typically, small d will be, quite a few magnitudes smaller than large d, and that allows us to make this approximation again, where the angle is essentially equal to tangent theta, and tangent theta is equal to y divided by the distance to the screen. Why are we so interested in these circular diffraction patterns? Well, again, as we stated at the beginning, the circular diffraction patterns are the type of diffraction patterns that we get from a circular objective lens or circular mirror. When we look at 2 points, we'll take a look at the simplest case that we can have, because again, when we're trying to resolve an image, the image actually consists of an infinite number of points, and these infinite points are really just small area disks. Let's say if we're looking at 2 stars in the sky, and the 2 stars are very, very close to one another, we're looking through a telescope. If they're very close to one another, the area disk will overlap, and it will be impossible to determine that we are looking at 2 objects rather than a single object. However, if we space the area disks far enough apart, such that the minima and maxima overlap, we get a pattern that looks like this. And this is the minimum criteria that we typically use for resolution. And again, it says that this angular resolution is equal to 1.22 times lambda divided by d. Now, this d, unfortunately, should be small d. That should be the diameter of the aperture. So if you're using a 60 centimeter, I have to use metric here, 60 centimeter objective lens in a telescope, that would be this diameter right here. The wavelength would probably be taken to be somewhere in the middle of the visible spectrum, so probably about half a micron, and then we would multiply that by 1.22. We're going to use some units of angular measurement that are a little uncommon. You're probably aware that a protractor has 180 degrees of angle. Basically, when you look at the sky from horizon to horizon, if it's unobstructed, is 180 degrees. We have 360 degrees in a circle. And each degree is essentially 1/360th of a full circle or rotation. Now, we can break the degree into even smaller units. If we take the degree and we break it into 60 equal units, we call these units arc minutes. Just like you can take an hour and you can break it into 60 minutes, we can break a degree into 60 arc minutes, or minutes of arc. Now, the full moon and the sun both have an angular size in the sky of about half a degree. So that gives them about 30 arc minutes in terms of their diameter. It changes because the Earth is in an elliptical orbit, the moon is in an elliptical orbit, so sometimes it's a little bit more, sometimes it's a little bit less. But in astronomy, a good rule of thumb is that 1/2 of a degree is about the size of the moon. So our arc minute, if we take our arc minute and then we break it into smaller units, we'll first of all blow it up right here. Here we have 1 arc minute. Just like the minute can be broken into seconds, we can break the arc minute into 60 arc seconds, or 60 seconds of arc. So we'll be using this when we're talking about the size of different objects and the resolution of different systems. The degree is the largest measurement of angle that we use. It's rather large when you think about it. The moon is a rather large object in the nighttime sky. So at half a degree, degree is really a little bit too large to talk about when we're typically pulling out a telescope. Arc minutes and arc seconds, which are finer measurements, are a little bit more appropriate. Now, when we use a telescope, one of the things that we face is the turbulence in the upper atmosphere. This is known as atmospheric seeing, or really, atmospheric seeing is the smallest object you can see, the best resolution that you can see for a given night. Sometimes when the sky is turbulent, the seeing will be poor, and maybe you'll get, well, resolution or seeing of about 5 arc seconds or 6 arc seconds. Really good seeing would be about 1 arc second, which means that the limiting factor of the turbulence in the atmosphere, the distortion due to moving air, can limit how far we can see down to as 1 arc second. So if you think about a degree, that's 1/3600th of a degree. That's pretty good when you think about magnification. What about our eye? Let's use our eye as an example. The average pupil size for our eye is about 3 millimeters, okay? It does get larger at night. Our pupil actually accepts more light in, but the problem is that as our pupil gets larger, these are in lower and lower light situations. We are using, rather than the cones, which are concentrated in the macula of the eye, we're using rods, which don't provide as high of a resolution. So really, your best resolution happens right around where your pupil is expanded to about 3 millimeters, where you have enough light to stimulate the cones. Now, if we do our calculation, we want to see the minimum resolving power of our eye. Again, we take the middle of the spectrum, about half a micron, as being the wavelength of light. We take the diameter of our pupil to be, again, 3 millimeters. And when we do this calculation, we get a result in radians, 1.66 times 10 to the minus 4 radians, okay? So that would be 0.167 milliradians. If we were to convert that to degrees, that's 0.0095 degrees. If we multiply that by 3,600, we get 34 arc seconds. Just for comparison, this shows us that we can see the moon pretty well. In order to resolve the moon in the sky, we need a resolution, a minimum resolution of about half a degree, okay? But our eye is certainly capable of seeing down to 0.0095, round that up to 1. We have about 50 times the resolution needed for the moon, or we can resolve objects on the moon, which are about 1/50th of the diameter of the moon. If we use a telescope, however, we can see that the resolution becomes much better. Now, think about resolution. This angular resolution, a smaller number, represents a more powerful telescope or more powerful optical instrument. It's allowing you to see smaller and smaller detail. Because after all, that's what we're doing. When we use a telescope or a microscope, we're looking at finer and finer detail. So the smaller we can make this number, the smaller the object that we can resolve. Now here we have an 8-inch celestron telescope, okay? This is what we have in the physics department here at NJCU. And the size of the objective lens, actually the corrector lens is 8 inches. The size of the mirror is 8 inches or 0.203 meters. Okay, so I'm going to plug that into my equation right now. It's quite a bit larger than the size of my pupil. And I notice that I'm down to 2.46 microradians, or less than 1 arc second. Now, again, remember our eye could see down to 34 arc seconds. Here, we're down to about 0.62 arc seconds. So this is a great telescope for amateurs to use. And really, because in most locations, the seeing, let's go back to the seeing right here, the best seeing that we can get is about 1 arc second, which means the atmosphere is going to jumble the image, such that we can't see anything finer than that. An 8-inch telescope is going to be, quite good for looking at different objects. Really, all a larger telescope is going to give you in a typical location is more light gathering capability. It's not going to give you better resolution because we have to see through the atmosphere. That's where adaptive optics comes in. We can go to certain locations, such as in Hawaii, on the Canary Islands, or in Chile, where the atmosphere is actually much more still, and obviously we're on a mountaintop, much thinner, so we don't get as much atmospheric turbulence. Well, it doesn't disrupt the image as much. And again, the world's largest telescopes are placed at this location. And these telescopes are 10 meters or larger. The Keck telescopes in Hawaii are 10 meters in diameter. The telescope in the Canary Islands, I believe, is 11. And then there's also a telescope in Chile, which is over 10 meters in diameter. Now, the way that these telescopes get beyond the atmospheric seeing and try to get pretty close to what resolution they're capable of is they use a laser. This is a yellow laser right here, and it's focused onto a layer of sodium atoms, which are high up in our atmosphere. And sodium glows, it's called the sodium D line. Sodium glows at this wavelength. And by shining on these sodium atoms, we can actually see how the light which is reflected by them is distorted by the atmosphere in between. So these telescopes play a little bit of a trick. Now, here are our wavefronts, and our wavefronts coming from a distant object we know should be nice planes coming in, and then they'll be focused onto a piece of film, an eyepiece, or some other detector. But this distortion created by the turbulence is going to effectively reduce our ability to really get fine detail. So the lasers give us a snapshot of what the atmosphere is doing. This is sent to sensors, which will then deform a mirror. The mirror, basically, what it does is it reshapes the waves. Some of the wavefront has gotten ahead, some of the wavefront has gotten behind. So if we match this distortion to this deformable mirror, we flatten out the waves, and basically that can then be sent to a camera, and we can get very, very close to the maximum resolution that telescope is capable of. The one problem that we have is we're only illuminating a very small part of the sky. So when we're taking images, we're taking images over a very, very small region. Okay, we can't get huge, large pictures when we do this. We pretty much have to focus on an individual object because we can't really take up, a large, swath of the sky and correct for that distortion. What if we want to completely eliminate all the contribution from the atmospheric turbulence? Well, easiest way to do this is to put a telescope up into space, and that's exactly what the Hubble Space Telescope did. Even though its mirror is only 2.4 meters, it outperforms these 10-meter telescopes pretty well. Even with the adaptive optics, it's pretty much the Hubble winning out, especially for much larger fields. Now, the Hubble Space Telescope operates between 100 nanometers, which is near UV, into some infrared parts of the spectrum. So I'm going to cheat here and say, okay, what is the maximum resolution we can get from the Hubble? I'll use the 100 nanometer light. And if I take a look at this, I can see that, again, with atmospheric seeing, 1 arc second is about what we get for uncorrected light. Here we can get down to 0.05, or, approximately 20 times better than what some of the best seeing would be. And you can see this is written as 52 MAS. That stands for 52 milliarc seconds. Going back to what we can achieve here, the scopes should have a resolution of about 12 milliarc seconds. I'm sorry, the correction that we get is between 30 and 60 milliarc seconds. And for Hubble, it can do pretty well. Of course, the James Webb Space Telescope is one of the most recent telescopes that was put into operation. Its mirror is much larger. The only problem here is it operates at longer wavelengths. It's designed to operate in the infrared. So we're getting the advantage of a bigger diameter mirror, but we're losing some of the advantage we have of the smaller wavelengths. Because infrared can actually penetrate through things like gas and dust, infrared is a better wavelength to use. It also, due to the Doppler shift of very, very distant objects, allows us to see features in the early universe which have been shifted to the infrared. So plugging numbers here, let's say that we're operating at 600 nanometers, which is the minimum wavelength of the Webb Space Telescope. Its gold mirror doesn't reflect very well at any shorter wavelengths. Here we can get down to about 0.023 arc seconds, or 23 milliarc seconds. Now, one strange thing that we have with the Webb Space Telescope, let's call it an artifact, is due to the fact that, first of all, we don't have a circular aperture. We have, well, roughly a hexagonal aperture. And that's going to produce a slightly different pattern than the traditional airy disk. We also have on this telescope the light being reflected to this secondary mirror, which then reflects it back to the instruments. Now, to support the secondary mirror, there's actually 3 different supports. There's a tripod right here. And if we look at the shadow that the central mirror and the associated tripod would have if cast on the mirror, this is essentially what we're going to get as a diffraction producing opening, that the light will be reflected in these yellow areas right here, but not reflected where the black is. Remember our single slit diffraction patterns where we pinch them down to a particular distance and that the diffraction pattern spread out in that direction? So for instance, if the smallest width was in the X direction, the diffraction pattern would spread out in the X direction. Well, here we're getting basically the same thing. The hexagonal pattern of the mirror produces these hexagonal spikes. So it's the minimum distance from here to here, okay, is most likely represented by this spike right here. And then the distance from here to here is going to produce this spike right here. So first of all, we get this hexagonal spike, but we also get, due to this central support right here, this support right here, another diffraction pattern in the horizontal direction. So that's how we look at these images and we see these very complex diffraction spikes on overexposed stars. Now, normally, if we're looking at things of less intensity, the diffraction effects don't really affect the overall image. What they do is they create an overall background brightness that can be subtracted off. But very, very intense objects such as stars are going to produce these diffraction patterns, which actually give it a very, very beautiful look. Now, we can actually play a game and increase our resolution even more than we can with a single object, okay? And again, James Webb Space Telescope, we have one mirror. The Hubble Space Telescope, one mirror. This pair of telescopes right here, and I believe these are the telescopes in Chile, but I can't remember which one they are. It's either the Canary Islands or Chile. Notice they have the two telescopes very close to one another. What they want to do at some point is be able to integrate the two together to basically use them as one larger telescope. This process is known as interferometry, where we take more than one device, we couple it in with another device, and it gives an effective aperture size much larger than the original aperture sizes. So in interferometry, our resolution is not limited by the size of the telescopes that we use, the size of the objective mirrors. It's limited by the baseline, the distance between the telescopes, okay? Now, interferometry is very, very difficult to do at wavelengths in the visible part of the spectrum. Okay, you've got to recombine the light, and essentially converting the interference pattern that we get is a very, very difficult process. If we could record the wavefronts in real time and process them in real time, we could produce a very, very powerful optical telescope. However, at this point, the technology, we do some optical interferometry. I know anybody who does work in interferometry would be upset if I said this. We can do some crude interferometry in the optical part of the spectrum, but if we want to do interferometry and get a high quality image, the radio part of the spectrum, where the frequency is much lower and the processing power doesn't have to be quite as high, is much easier to do. Now, again, we have the disadvantage that we're going to a longer wavelength, and that means that that's going to hurt our resolution. But this is a very large array. It has a 36-kilometer baseline in its largest configuration, and it's actually in New Mexico. It operates at a wavelength of 1 centimeter. So again, I'm going to do my little equation right here for minimum resolution. Again, we have 1.22. On the upper part, I have 1 centimeter. And remember, in visible light, this is 5 times 10 to the minus 7. Now we're talking about huge waves here in comparison, huge wavelengths in comparison to what we had before. But now we're making the baseline much bigger. Instead of talking about a telescope with an objective in meters, we're talking about a baseline in kilometers. And as you can see here, this very large array has a pretty good resolution, okay? You can see down to 70 milliarc seconds. And just to remind you where we were with some of the other telescopes, Webb Space Telescope, 23 milliarc seconds. Hubble telescope, 52 milliarc seconds. So down to 70 milliarc seconds, it's pretty comparable. And again, we're looking at a very different part of the electromagnetic spectrum. So we're seeing in the radio part of the spectrum. Now, the Event Horizon Telescope. This was one of the greatest feats of interferometry, in my opinion, that was ever performed. What they did is they used telescopes throughout the world to create one big interferometer. Now, once again, the problem is, the whole idea of an interferometer is you need to have the phase information from the wavefront at each location in real time. You can combine them together to produce well, kind of produce an image, but you need the phase information to basically get any meaningful information. So what that required was all these different radio telescopes operate throughout the world, even one down in Antarctica. Instead of having them communicate with one another in real time, they recorded the radio waves on hard drives. These wavefronts involve so much information, you can't just simply send them over some communication signal. It actually had to be written onto hard drives where they had to keep very, very accurate track of time as the recordings were being made. Now, this provides a huge baseline, 1.27 times 10 to the 7 meters, for what they call the Event Horizon Telescope. It is not a single telescope. It's many telescopes operating throughout the world at the same time. It's sort of a virtual telescope, if you will, where the information was then recorded and then sent to a location to be basically broken down or analyzed at some later time. And you can see here, this achieved a resolution of 0.20 milliarc seconds. Let's go back. The Very Large Array, which was actually part of the Event Horizon Telescope, 70 milliarc seconds. Webb Space Telescope, 23 milliarc seconds. Hubble, 52 milliarc seconds. These are all in the tens of milliarc seconds. Here they were able to achieve a resolution in the tenths of an arc second. And why is it called the Event Horizon Telescope? Because they were trying to image for the first time the accretion disk around the black hole, where the event horizon would basically create what effectively is a shadow. And here you can see one of the lead researchers with all the different hard drives in one place. And these are massive hard drives containing 5 petabytes of information. So if you go computer shopping and you buy a really high-end computer, maybe it'll have a terabyte on it. Okay, so the analog radio signal was basically, its phase and amplitude was stored on these. So 5 petabytes represents 5,000 terabytes of information. Again, too much information to send in real time. So again, it was stored on a hard drive and then shipped to a lab to be correlated. And then after the information was processed, we got an image of a black hole. And again, the event horizon is the point around the black hole where even light can't escape. And you need a much higher resolution than is possible with even the most powerful telescopes in order to resolve this. And even with that incredible resolution, you could see that the image is pretty fuzzy. Okay, so we're really at the resolution limit here. And again, the event horizon would actually be somewhat smaller than the shadow that it casts. And then this right here, this bright part, which was giving off the radio waves, that is the very hot plasma in the accretion disk, which is spiraling into the central black hole at the center of a large galaxy by the name of M87. Let's talk about something a little more terrestrial, the microscope. We also have to worry about resolution when we're talking about a microscope, but we approach this in a slightly different way. The resolution for a microscope actually depends on something called the numeric aperture, okay? The numeric aperture is the index of refraction through which the light is passing through, times sine theta. Theta is the angle at which the light is leaving the object that you're imaging, or basically the angle of the light which can be captured by the objective lens. All right. And D is the smallest object that you can see. Sorry, I'm using so many D's. D represents the diameter of the aperture. Sometimes D represents the distance of the screen. This D represents the distance that you can resolve, the smallest object that you can resolve, and that's equal to the wavelength of light divided by twice the numeric aperture, okay? So if I can make this angle larger and larger, I can make the object size that I can image smaller and smaller. One important thing you see here is that this wavelength is very, very important to the size of what you can image. The general rule of thumb is you can't really get a resolution. There's some tricks you can play, but you can't really get a resolution better than the wavelength of light. And one thing that we do with the microscope when we're going to really, really high powers is we take a lens with a very, very large numeric aperture. Look at this. This angle right here is we're trying to get as close to 180 degrees as possible. But the other thing that we attempt to do is I see that in this numeric aperture equation, the index of refraction is there. So if I surround this lens with a high index of refraction material, I can actually boost my resolution by not much, but a little bit, enough to be worth doing it. So what I do is I use a high index of refraction oil there, and we call these oil immersion lenses. And again, if you're going from an index of refraction of 1 to 1.7, you're increasing your potential resolution, you're improving your resolution by about 70%. CDs and DVDs. CDs are an older technology. DVDs are more recent technology, but we'll also talk about Blu-ray here. Now, we can store data a number of different ways. We can store it on magnetic media, which has been done for a very long time. We still do that today. It used to be magnetic tape, nearly half a century ago. We went to magnetic discs, which we still use today. We use flash memory, which is an electronic media, and there's actually optical media that we can also use. And basically, pits are imprinted onto a rotating disc, which a laser is going to read. Now, originally, the CDs, called compact discs, used infrared light and focused the infrared light onto the disc. And the pits would basically be bumps that would either reflect the light or not reflect the light. So as the optical disc is rotating, the pits would change the alignment of the reflection, and you could basically assign a reflection as being a 1 or a non-reflection as being a 0. I'm not quite sure what the encoding is on these, but as you can see, as it's rotating, you're going to change the way that the light is being reflected. Now, again, basically the way that this worked is you have this rotating disc, so any vibrations could create an error very easily, and tracking these things has become better and better. But with the original infrared light, you didn't have to be as accurate, because you would basically focus the light down to a nearly diffraction limited spot size, and that's as small of a pit as you can use. So the original CDs would have rather large pits, but we'd also use diffraction gratings to spread the beam into multiple beams, and that would allow us to correct for any error. You can have the m equals 0 beam, then m plus 1, m minus 1, and with multiple sensors, you could see if there were any errors there. So again, this would give you some tolerance in terms of tracking if you're a little bit off. The size between different grooves, if that's what you want to call them on a CD, was about 1.6 microns. And again, the spot size was, probably approaching probably approaching about 1 micron. And by placing them through plastic, you could actually get a smaller spot size. In air, the index of refraction is 1. As it propagates through the plastic, the wavelength actually gets shorter, which allows you a smaller spot size. So again, reading a CD was really quite easy. A laser beam would be set at some radius from the center of the disc. The disc would spin, and as it would spin, you would get alternating flashes of light or lack of light due to the pits. Now, eventually, the CD was replaced because it really didn't store as much information. I'm sure if you can get, I'm sure you can probably still get CD readers, but we switched the wavelength to a shorter wavelength with DVDs, which can also read older CDs. And what that allowed you to do is just get a smaller beam size. Smaller beam size meant that you could get smaller pits. Smaller pits meant that you could store more data on the disk. And as the technology improved, you could also read the information much faster as the disk would spin faster. Eventually, we went to an even shorter wavelength. It says Blu-ray. Okay, it's actually in the violet part of the spectrum, but at 405 nanometers, the pits could be even smaller. And of course, we could store much more information as a result. So here are the basic standards which have been used for optical data storage, and the effective pit sizes. Once again, at 780 nanometers, your spot size would be somewhere around 1.6 microns. The pits themselves would be about the size of about 800 nanometers. So that would be really the limiting factor of how much information you could store there. Once they went to the DVD, you could actually do two things. And not only could you make the pits smaller, you could also use multiple layers. And basically what you're doing here is you're using all 3 dimensions. You could focus the light on different layers within the disk, and they could even make these double-sided. And with smaller pits, with multiple layers, you'd be able to increase the amount of data stored. Now switching to shorter wavelengths, the amount of information can be increased even more. Remember, you might think that a change from 780 nanometers to 650 nanometers isn't going to give you all that much more capacity. But really, in terms of the area of the spot size, the area of the spot size goes by the square of the wavelength. So if you decrease your spot size by 40%, okay, 1.4 is the square root of 2, you're doubling your data storage per unit area. Okay, so again, the switch to the shorter wavelengths has created a higher density for optical storage. And again, it's about diffraction, that even though these lasers, okay, these are diode lasers, so they're leaving a very, very small bit of semiconducting material, but they are exiting the edge. Basically, the openings are sort of square. The beam itself is somewhat elliptical. We can approximate the aperture of these lasers, to be circular.